Hello everyone, this is Subashini GS, currently pursuing BE in Computer Science and Engineering in SETHU Institute of Technology. I have been given a topic Hadoop in Big Data to create a seminar video. Let's get into the topic. At the end of this tutorial, you will come to know about what is big data, applications of big data, what is Hadoop, sub-projects of Hadoop, Hadoop architecture, topology used in Hadoop, and features of Hadoop. Now, what is big data? Big data is a collection of data that is huge in volume yet growing exponentially with time. It is a data with so large size and complexity that none of the traditional data management tools can store it or process it efficiently. Big data is also a data but with huge size. Following are some of the applied areas of big data: banking and securities, communications, media and entertainment, healthcare providers, education, manufacturing and natural resources, government, and insurance. What is Hadoop? Apache Hadoop is an open source software framework used to develop data processing applications which are executed in a distributed computing environment. Applications built using Hadoop are run on large datasets distributed across clusters of commodity computers. Commodity computers are cheap and widely available. These are mainly useful for achieving greater computational power at a low cost. Similarly, to data residing in a local file system of a personal computer system, in Hadoop, data resides in a distributed file system which is called as a Hadoop distributed file system. The processing model is based on data locality concept, wherein computational logic is sent to cluster nodes containing data. This computational logic is nothing but a compiled version of program written in a high-level language such as Java. Such a programming process data stored in a Hadoop HDFS. Apache Hadoop consists of two sub-projects: Hadoop Map Projects, Hadoop Distributed File System, that is HDFS. Hadoop MapReduce. MapReduce is a computational model and a software framework for writing applications which are run on Hadoop. These MapReduce programs are capable of processing enormous data in parallel on large clusters of computation nodes. HDFS, Hadoop Distributed File System. This takes care of the storage part of Hadoop applications. MapReduce applications consume data from HDFS. This creates multiple replicas of data blocks and distributes them on compute nodes in a cluster. This distribution enables reliable and extremely rapid computations. As we all know, Hadoop is a framework written in Java that utilizes a large cluster of commodity hardware to maintain and store big size data. Hadoop works on MapReduce programming algorithm that was introduced by Google. Today, lots of big brand companies are using Hadoop in their organization to deal with big data. Example: Facebook, YouTube, Netflix, eBay, etc. The Hadoop architecture mainly consists of four components: MapReduce, Hadoop distributed file system, yet another resource negotiator, common utilities, or Hadoop common. Let's understand the role of each one of this component in detail. MapReduce. MapReduce nothing but just like an algorithm or data structure that is based on Yarn framework. The major feature of MapReduce is to perform the distributed processing in parallel in a Hadoop cluster, which makes Hadoop working so fast. When you are dealing with big data, serial processing is no more of any use. MapReduce has two main tasks which are divided phase-wise. In first phase, map is utilized and in next phase reduce is utilized. Here we can see that the input is provided to the map function, then its output is used as an input to the reduce function, and after that we receive our final output. Let's understand what this map and reduce does. As we can see that input is provided to the map function. Now as we are using big data, the input is a set of data. The map function here breaks this data blocks into tuples that are nothing but a key value pair. These key value pairs are now sent as input to the reduce function. The reduce function then combines these broken tuples or key value pairs based on its key value and forms set of tuples and performs some operations like sorting, summation type job, etc., which is then sent to the final output node. Finally, the output is obtained. The data processing is always done in reducer depending upon the business requirement of that industry. This is how first map function and then reduce is utilized one by one. Let's understand the map task and reduce task in detail. Map task. Record reader. The purpose of record reader is to break the records. It is responsible for providing key value pairs in a map function. The key is actually is its locational information and value is the data associated with it. A map is nothing but a user-defined function whose work is to process the tuples obtained from the record reader. The map function either does not generate any key value pair or generate multiple pairs of these tuples. Combiner is used for grouping the data in the map workflow. It is similar to a local reducer. The intermediate key value that are generated in the map is combined with the help of this combiner. Using a combiner is not necessary as it is optional. Partitioner is responsible for fetching key value pairs generated in the mapper phases. The partitioner generates the shards corresponding to each reducer. Hash code of each key is also fetched by this partition. Then the partitioner performs its hash code modulus with the number of reducers, that is key hash code percentile number of reducers. Reduce task. The task of the reducer starts with a step shuffle and sort, the process in which the mapper generates the intermediate key value and transfers them to the reducer task is known as shuffling. Using this shuffling process, the system can sort the data using its key value. Once some of the mapping tasks are done, shuffling begins. That is why it is a faster process and does not wait for the completion of the task performed by the mapper. The main function or task of the reducer is to gather the tuples generated from the map and then perform some sorting and aggregation sort of process on those key value depending on its key element. Once all the operations are performed, the key value pairs are written into the file with the help of record writer. Each record is in a new line and the key and the value is a space is matter. Hadoop distributed file system is utilized for storage permission. It is mainly designed for working on commodity hardware devices working on a distributed file system design. HDFS is designed in such a way that it believes more in storing the data in a large chunk of blocks rather than storing small data blocks. HDFS is in Hadoop provides fault tolerance and high availability to the storage layer and the other devices present in the Hadoop cluster. Data storage nodes in Hadoop HDFS are name node, that is a master node, and the data node called as a slave node. Name node works as a master in a Hadoop cluster that guides the data node. Name node is mainly used for storing the metadata, that is the data about the data. Metadata can be the transaction logs that keep the track of the user's activity in a Hadoop cluster. Data node works as a slave. Data nodes are mainly used for storing the data in a Hadoop cluster. The number of data nodes can be from 1 to 500 or even more than that. The more number of data node, the Hadoop cluster will be able to store more data. So it is advised that the data node should have high scoring capacity to store a large number of file blocks. Data in HDFS is always stored in terms of blocks. So the single block of data is divided into multiple blocks of size 128 MB, which is default, and you can also change it manually. Let's understand the concept of breaking down of file in blocks with an example. Suppose you have uploaded a file of 400 MB to your HDFS. Then what happens is this file got divided into blocks of 3 in multiples of 128 MB and 16 MB file, totally 400 MB sized file. Means 4 blocks are created, each of 128 MB except the last one. Hadoop doesn't know or it doesn't care about what data is stored in these blocks. So it considers the final file blocks as a partial record, as it does not have any idea regarding it. In the Linux file system, the size of the file block is about 4 KB, which is very much less than the default size of blocks in the Hadoop file system. Read and write operations in HDFS operate at a block level. Data files in HDFS are broken into block-sized chunks, which are stored as independent units. Read operations in HDFS. Data read request is served by HDFS name node and data node. Let's call the reader as client. The diagram depicts file read operations in Hadoop. A client initiates a read request by calling open function method of file system object. It is an object of type distributed file system. This object connects to a name node using RPC and gets metadata information such as the locations of blocks of the file. Please note that these addresses are of first few blocks of a file. In response to this this metadata request, addresses of data nodes having a copy of that block is returned back. Once addresses of data nodes are received, an object of type FS data input stream is returned to the client. FS data input stream contains DFS input stream, which takes care of interactions with data node at name node. In step 4, shown in the diagram, a client invokes the read method, which causes DFS input stream to establish a connection with the first data node with the first block of a file. Data is read in the form of streams, where its client invokes read method repeatedly. This process of read operation continues till it reaches the end of the block. Once the end of the block is reached, DFS input stream closes the connection and moves on to locate the next data node for the next block. Once the client has done with the reading, it is called close method. Write operation in HDFS. A client initiates write operation by calling create method of distributed file system object, which creates a new file. Step number 1 in the given diagram. Distributed file system object connects to the name node using RPC call and initiates a new file creation. However, this file creates operation does not associate any block with the file. It is responsible of name node to verify that the file which is being created does not exist already and the client has a correct permission to create a file. If a file already exists or client does not have sufficient permission to create a new file, then IO exception is thrown to the client. Otherwise, the operation succeeds and a new record for the file is created by the name node. Once a new record in the name node is created, an object of type FS data output stream is returned to the client. A client uses it to write the data in the HDFS. Data write method is invoked in step 3 of the diagram. FS data output stream contains DFS output stream object, which looks after the communication with the data nodes and the name nodes. While the client continues writing, DFS output stream continues creating packets with this data. These packets are enqueued into a queue, which is called as data queue. There is one more component called data streamer, which consumes this data queue. The data streamer also asks name node for allocation of new blocks, thereby picking desirable data nodes to be used for replication. Now, The process of replication starts by creating a pipeline using data nodes. In our case, we have chosen a replication level of 3 and hence there are 3 data nodes in the pipeline. The data streamer pours packets into the first data node in the pipeline. Every data node in a pipeline stores packet received by it and forwards the same to the second data node in the pipeline. Another queue, ACK queue, is maintained by DFS output stream to store packets which are waiting for the acknowledgement from the data nodes. Once acknowledgement for a packet in the queue is received from all data nodes in the pipeline, it is removed from the ACK queue. In the event of any data node failure, the packets from this queue are used to reinitiate the operation. After a client is done with the writing the data, it is a close method. Step 9 in the diagram, call to close, results into flushing remaining data packets to the pipeline, followed by waiting for acknowledgement. Once a final acknowledgement is received, name node is contacted to tell it that the file write operation is complete. The next component of the Hadoop architecture is YARN, that is yet another resource negotiator. YARN is a framework on which MapReduce works. YARN performs two operations that are job scheduling and resource management. The purpose of job scheduler is to divide a big task into small jobs so that each job can be assigned to various slaves in a Hadoop cluster and processing can be maximized. Job scheduler also keeps track of which job is important, which job has more priority, dependencies between the jobs, and all other informations like job timing, etc. And the use of resource manager is to manage all the resources that are made available for running a Hadoop cluster. The following are the features of the YARN, yet another resource negotiator: multi-tenancy, scalability, cluster utilization, and compatibility. These are the features of the YARN network. The fourth component of the Hadoop architecture is Hadoop Common or Common Utilities. The Hadoop Common or Common Utilities are nothing but our Java library and Java files, or we can say that JavaScripts that we need for all the other components present in a Hadoop cluster. These utilities are used by HDFS, YARN, and MapReduce for running the cluster. Hadoop Common verifies the hardware failure in a Hadoop cluster is common, so it needs to be solved automatically in software by Hadoop framework. The topology or arrangement of the network affects the performance of the Hadoop cluster when the size of the Hadoop cluster grows. In addition to the performance, one also needs to care about the high availability and handling of failures in order to achieve this Hadoop. Cluster formation makes use of network topology. Typically, network bandwidth is an important factor to consider while forming any network. However, as measuring bandwidth could be difficult, in Hadoop a network is represented as tree and distance between nodes of this tree, that is the number of hops, is considered as an important factor in the formation of Hadoop cluster. Here the distance between two nodes is equal to the sum of their distance to their closest common ancestor. Hadoop cluster consists of a data center, the rack and the node which actually executes the jobs. Here data center consists of racks and rack consists of nodes. Network bandwidth available to process varies depending upon the location of the processes. That is, the bandwidth available becomes lesser as we go away from processors on the same node, different nodes on the same rack, nodes on different racks of the same data center, nodes in different data centers. The following are the main features of the Hadoop: open source, highly scalable cluster, fault tolerance is available, high availability is provided, cost effective. Hadoop provides flexibility and it is easy to use. So here we have reached the end of this video. So from this video you came to know about the definition of big data, the areas where the big data technology is used, and architecture used in big data, that is Hadoop and its sub projects, architecture of Hadoop and advanced architecture of Hadoop, the network topologies used in Hadoop architecture, and the main features of Hadoop. Hope this video is useful for you. Thank you for your patience.